is we would be recapping about the sessions 1 and 2 a little bit, and then we'll talk about feature engineering and the word vectorization techniques. And those are n-grams, pack of words, TF-IDF, word to vec. We would also see that in Google Colab as a demo, and then we'll just recap. So in session 1 and 2, we talked about natural language processing, what NLP essentially is, and how it is different from the other fields. So AI is the main field, and there are subfields like machine learning and deep learning, and NLP have some intersections between ML and DL, but it's not totally the same. It has some differences as well. So far, we discussed about pre-processing and we discussed about punctuations, stop words, stemming, and lemmatization. So we talked about how to bring back the word in the root form using stemming and lemmatization, and how to uh, prepare the data set and ignore the irrelevant information by removing stop words. Today, we are going to talk about feature vectorization. And after that, in the coming sessions, we would be talking about classification, in which we would be using both pre-processing and feature extraction to do the predictions. So the NLP pipeline look like this. So there is text pre-processing, in which we clean the text, we stem the text, and we essentially bring back to the normal form. And we remove the unnecessary words, we remove the special characters because they do not add anything special to the information. So those are the irrelevant information that we can discard. Then we perform EDA, which is exploratory data analysis, in which we essentially see that how is the structure of the data, what is the distribution of the labels, how our data looks like, so that we can find anomalies and we can find the pattern in the data, and we can visually see that how our data is in real. Um, and then comes the representation, which is nothing but word vectorization, because this is how we are going to represent our data set, because machines and algorithms cannot process the data directly, which is in the textual form. It needs to have a certain format, and that is what we are going to achieve with word vectorization, and that's what representation is. So we tokenize the data, that is, we divide the sentences in the individual words, and then we convert those words into a numerical form. And padding sequences is also a part of representation, which is used to prepare the sentences in a particular length. So let's say I have multiple sentences, and some of them are like of a particular length, and some of them are of a different length. So there is no fixed length. But while padding, I would make sure that ultimate encoded sentence would have the similar length. So if my one sentence is of length 5 and another sentence is length 10, then while encoding I would make sure that I am padding the first sentence with 5 places, so that it also becomes with the length of 10. So that's what padding is. Then in the future sessions, we would be talking about modeling. And then there is also deployment, that let's say you have prepared the whole model, you already have a working project, but you want the user to access it. So for that, you would be deploying that on web, and you can use multiple technologies. And most famous for that, so for most famous technology for machine learning projects is Flask. So Flask is mostly used for deployment, and that is also something that you can look into. So let's talk about feature engineering first. So feature engineering is basically converting the sentences in the textual form in the numerical form. So as I told you that machine learning algorithms cannot work on the raw data directly, and you have to process that and prepare that into a numerical form. So that's what we are going to do with feature engineering. So this converts the text into a matrix or a vector form, and there are popular methods to do this, and some of them are bag of words and TF-IDF. We would be talking about this later. Uh, so as you can see on the right hand side, this is one example. So this is the sentence, the cat sat on the mat, and we are providing 1 and 0 labels according to the word present in a column. So for each word, there is a separate column. So for the, we have this column, and the is present. So we are going to put 1 and 0 elsewhere. Similarly, for the cat, we are going to put one where the cat is present and 0 elsewhere. So in this form, we are going to prepare the metrics, and this would convert the sentence in the textual form to the numerical form. And this would be easy to process by the algorithm. So let's talk about the differences between syntax and the semantic. So the sentence is formed by using both syntax and semantic analysis. So syntax and structure are codependent. A set of specific rules and conventions are used. So for preparing a particular sentence or preparing a paragraph, you have to follow certain rules and forms of that particular language. So talking about English, we have to take care of how the word adjectives and verbs and other things are going to be assembled to form the sentence. So even if the word is correct syntactically, it doesn't mean that it would be correct semantically. So while forming the sentence, both of these things are important to taken into consideration. So unordered words do not convey much information. As you can read the text over here, the dog, the over, he, lazy, jumping. So this doesn't make any sense. So for that to make sense, we have to take care of the semantics as well. So, talking about the differences, syntax is the grammatical structure of the text, and semantics is the meaning conveyed. Uh, so, let's say here is the sentence called "Call me cab." This is syntactically correct, but it's not making sense. So, we have to take care of the semantic stuff as well. So, okay, you are a cab. So that doesn't make any sense at all. So, sentence that is syntactically correct may not always be semantically correct. Syntactic analysis basically assigns a semantic structure to the text, and semantic analysis is the process of understanding the meaning and interpretation of words, signs, and sentences structure. So not only the call me cab example, there could be any example. So let's say there is another example, cats flow supremely. So it's grammatically valid, but it does not make any sense. So in machine learning, we have to take care of both of these things, both syntax and the semantic. So let's talk about the first technique, which is n-grams. So what is n-grams? So n-grams is a language model, and it basically depends on the previous words. So the coming word, the word that would be coming in the later uh, part of the sentence would be depending on what previous words we have seen so far in that particular sentence. So it particularly finds the probability distribution over word sequences. So here n-grams represents the sequence of n words. So n could be anything. It could be two, it could be three, or literally anything. We essentially cut out the noise from the data with this technique, and we identify the themes quickly. So multiple applications are there for this technique. There could be speech recognition, there could be machine translation, or there could be predictive text input. So there are two approaches to the n-gram technique. So the first one is not really efficient, but let's talk about it. So to calculate the probability of a given word, we take the history into consideration. So if there's a sentence, today the sky is so clear that, and we want to predict the probability of the word coming, the word the to be coming after this sentence. So for that, we are going to take a large corpus. We are going to count the number of times the uh, sentence today the sky is so clear that appears, and then we are going to count the it number of times the has occurred when we already have this sentence in the history. So the probability would be equal to the count that the today the sky is so clear that the has come, given we already have today the sky is so clear that. So for a particular word, in this case the, we are taking into consideration the whole history, and that's how we are going to know that what is the probability that we are going to get the in this case. So as I told you that this technique is not really efficient when we have a large corpus. So corpus is essentially a data set, and when we have a large data set, this would not work in real world, because we have to go over the entire corpus again and again for a particular word. For calculating a particular probability, we have to take consideration of the whole history, and that's not feasible at all. So for that, to overcome that, there is another technique, and in that we make use of the chain rule. So instead of taking consideration of the whole history, we just consider few words as history. So in this case, we are talking about the. So we want to calculate the probability of the when we already have the history. But let's say we are not talking about the whole sentence. We are just talking about the previous word that occurs previous to the. So previous to the, we have that. So let's take that only. And that prepares the bigram model, because in this case we are taking the and that. So this that approximates the probability of a word given all the previous words by using only the conditional probability of one preceding words. In this case, that. But we can also make this a little bit longer. So let's say we are not taking only that into consideration. We are also considering clear and that. So let's say calculating the probability of the when we already have clear that. So in this case, we have two words. So clear and that, two words to taking into consideration for predicting the probability of the. So in similar way, you can take any number of sequences, and that's what n-grams is about. So n is the number of sequences that you would be taking. So this is what we are talking about. So we have this word that is the in this case, and for predicting the probability for that, we are taking into consideration the previous words. The n minus 1 represents the previous word, which is that. So this is also Markov assumption. So assumption is that the probability of a word depends only on the previous words. Uh, so that's what we discussed just now. And these models are the class of probabilistic models that assume that we can predict the probability of some future unit without looking too far in the past. So earlier we were talking about the whole sentence, but now we are just talking about some words in the history, and that is still feasible, and that's not really inefficient. Another technique we are going to talk about is bag of words. So in n-grams, we were taking into consideration the previous words, the history. So we were talking about the structure somehow, but in the bag of words, we are just going to throw away the words as if we are throwing them into a bag, and we are not going to consider any structure at all. So any information about the order or structure of words is totally discarded. We are only concerned with whether the words known in the document are present or not. So it's all about the frequency. Now we are not bothered about the structure at all. We are just talking about what is the frequency of a particular word, how many times we have seen that in our corpus. And the intuition behind this is that the similar documents must have the similar content. So even if we are not considering this considering the history or structure, we know that similar documents must have similar content. So if two stories are same, the words must be uh, common in both of them, and that's what we assume here. So the intuition is that the similar content would be there. A very common feature extraction procedures for sentences and documents is the bag-of-word approach. And like I said, that we talk about the frequency of the words here. The bag-of-words can be simple or complex. That depends on what you assume. The complexity comes both in deciding how to design the vocabulary of known words or tokens. So when we divide the sentences into words, those are called tokens. And how to score the presence of known words is also part of the bag-of-words. So this is the most simple vector space representational model for unstructured text. So let's say your text doesn't have any structure, and to provide that into the vector space to see how that looks like in the vector space, we are going to use this technique. It's really simple, and it's mostly used when you're not going for the complex techniques. That's when the bag of words is used. The model's name is such because each document is represented literally as a bag of its own words, disregarding word orders, sequences, and grammars. So bag of words is one of the most fundamental methods to transform tokens into a set of features. The bag of word model is used in document classification, where each word is used as a feature for training like classifier. So for example, in a task of review-based sentiment analysis, the presence of words like fabulous, excellent, these indicates that there is a positive review, while the words like annoying and poor would point to a negative review. As you can see, so this is the raw text here. So it is a puppy and it is extremely cute. And to see that in the bag of word vector form, we can see that we are scoring that according to the frequency. So it occurs twice. So we have scored that as 2. They hasn't occurs they hasn't occurred here. So we have put 0 for there. Puppy and art were cute extremely. These have puns. So each text document is equal to numerical vector here. So each dimension is also equal to specific vector from the corpus. Uh, so this is about the pack of words. So this is another example from uh, Charles Dickens' book, and this is it was the best times, it was the worst time. So these are the sentences, and for the first step, we collect the data. We process the first few lines of the text from that book. Each line is treated as a separate document, and there are four lines, and that forms the entire corpus. So for now, we have a data set, and that only contains these four sentences, and each sentence is a different document. So we construct a list of all the words in the model's vocabulary. So separating the sentences in tokens, and then those tokens are being used as a vocabulary. And we are only going to take the unique words. So we don't want to make repetitive calls in our algorithm. So we are only going to take the unique words. And also we are going to ignore the cases and punctuations so that the final vocabulary that we have is clean. So out of the corpus of the 24 words, we are only taking 10 words here to see for an example. Uh, and now we are going to score those words in each document. So remember that each document is nothing but each sentence. And for accordingly, we are going to score the words based on the frequency they have, because that's what the bag of word model is. So document of free text is a vector, and vector is equal to the input or output of the model. So these are the 10 words that we are taking into consideration for the vocabulary, and we have scored them according to their frequency. So the words having one have occurred one time, and the words having zero haven't occurred in the vocabulary. So that's why they are being assigned zero. So the vocabulary size and the vector representation, like how large a vocabulary would be, depends on you. So it depends if you are removing the stop words or not, if you are cleaning your vocabulary or not. So the best practice is to treat every, like if the word is same and only the case is different, the best practice is to consider both of them as same. So let's say I have a word that have an uppercase, and then I have another word which is the same word but it's in the lowercase, but both of the words are same. So I would make sure that each and every word have the same case, so that the model is not considering those as two different words. So ignore the case, ignore the punctuations, ignore stop words, because those don't add anything to the information. And fix the misspelled words as well. Stemming is bringing the word back to the root form. So eating and other words would become coming back to the base form, which is eat. So this is how we would prepare the vocabulary, because now we are talking about each word separately, and that is how we are forming the vectors. So it's important that we are only considering the important words that we actually want to see in our vocabulary. The next technique is the TF-IDF technique. So in bag of words, we didn't have any structure. We just considered the frequency of the words. But let's see what happens in TF-IDF. So TF-IDF stands for term frequency, inverse document frequency. So it's essentially the combination of two metrics, which is term frequency, the first one, and the inverse document frequency, which is the second one. So it's mostly used in information retrieval. So the basic idea behind TF-IDF is uh, what if some words occur very rarely in the corpus, and those are not given importance because we are considering the frequency, and the least occurring words would not be given much importance because they are not occurring as frequent as the other words. But what if those are really important and we want to really consider them while creating the algorithm? And what if there are a lot of words which have higher frequency but doesn't have any information, and based on a particular corpus, those are not really important for the information? So in that case, we have to balance both of these things. We have to balance the importance of the rare words and also the non-importance of the words that are frequently occurring. So that's how TF-IDF algorithm is formed. So there are text documents again, and we form vector models based on the word occurrences without considering the exact ordering. So in this case as well, we are not considering the ordering as such. It doesn't matter which word comes before or after, but we are talking about how frequent that comes into the corpus. So given the data set of n text documents, TF and IDF are defined as follows. So TF is the count of a term T in our document D. So if I have a sentence and I am considering that as a document D, so each term and the count of that would be considered with T. An IDF is the logarithm of ratio of total documents T in the entire corpus and the number of documents D containing the term T. So it might seem mathematically heavy at first, but it's not that difficult to understand. Um, so together, the relative importance of a term in a corpus is observed. So that's what I discussed, that we have to balance both, like the frequently occurring words and the words that are occurring rarely. We have to balance both of them together. So this is how the mathematical equation would look like. So there is this word, let's say there is any word, and then TF would be the frequency of X in W, and DF would be the number of documents containing X, and N would be defined as a total number of documents. And when we take the log of this term and multiply that with the frequency of X in Y, we would get the TF-IDF of term X within the document Y. So there are some independent equations here. So there is this first equation where we are talking about the frequency of term I in document J, and n is the total number of words in the document J. So we are dividing this frequency with the total number of words. This would calculate the TF, the term frequency, and for the inverse document frequency, we are going to add 1 to the log of total number of documents in the corpus divided by the number of documents that contain that particular word I. And when we multiply these two terms together, we get the TF-IDF score of a particular term. So this takes care of both the words that are rarely occurring and the words that are frequently occurring. So there is a balance maintained. So the properties of this particular technique is, we this is computed for every word in every document, and the final result that we get is a matrix with the shape words into documents. So this is what the final shape of the matrix would look like. And a single value for one word would be matrix of values when considering all the documents. So this was a document, and in the vector space representation, this is how the term document matrix would look like. These are the separate words or tokens, and these are the document frequencies. So let's talk about it a little bit more with an example. So let's say we have three documents here, and documents are nothing but the sentences. So the first one is machine learning teaches machine how to learn. The second one is machine translation is my favorite subject. And the third one is term frequency and inverse document frequency is important. And now we are going to compute the Fij, which is the frequency of term I in document J as shown in equation 1. Uh, and this is how we are going to compute it. So, so this is for the equation 1. And then this is how we are going to calculate it further. So it might seem difficult to understand at first, but when compared to the bag of words model, it's still somehow better, because in bag of word models, when you have the words having higher frequency, uh, those words are given the most importance, and maybe those words are not really important in the corpus, and that is when TF-IDF balances both of the things together. So it's somehow better than the bag of words technique. So the second step after that is to compute the normalized term frequency, which is the TF-IJ in equation 1. And each word in a single document, which is sentence, should divide total words with the number of words in that document. And after dividing, we get these numbers for each of the words. Now compute the IDF. So we already have the TF now, but for the TF-IDF as a whole term, we need to multiply the TF with the IDF, and we are going to we are going to calculate about uh, IDF in the next slide. So this is how we are going to calculate the IDF using the equation 2 that we saw in the previous slide. So after calculating the IDF of these terms, next we are going to multiply those together to get the TF-IDF of each of the terms. So these are the individual terms and these are the TF-IDF scores for them. So let's say we have a query now, we have machine learning, we have these two words and we want to compute the TF-IDF. So you can see more clarity here. So machine would be given this TF score and that IDF score would be this. And after multiplying both of those terms, this would be the final TF-IDF score. And in terms of the documents, these three would be the numbers that we would be getting. This is in the terms of the sentences. Now let's talk about the most important and most efficient techniques. So we talked about n-grams, we talked about Pago words and TF-IDF. Those are helpful when we want to represent the words into the vector form, but the word to vec is the most efficient out of all of them. So in word to vec, we consider word embeddings. So we construct the word embeddings from the corpus we have. So word embeddings are nothing but the vector representations of a given word. So with words having similar meaning, they should have the similar representation as well. So let's say there are multiple words. Those words might seem different, but if they have the same meaning, they should be put in a particular space, because if they mean if they mean the same thing, they should be present in the same space. So it's all about the representation. In word embeddings, we form the vector space according to the representations based on how similar or different the words are. So we capture the properties of a word in a particular document. So in this case, we consider the context, the semantic, the syntactic similarity, and the relation to other words. So in the previous techniques, in particular techniques, we were not considering the structure at all, and in some techniques we were considering the structure, but we were not taking into consideration both the semantic and syntactic similarity. But in this case, we are going to take all of them into our consideration and then form the vectors. So we talk about the context as well, we talk about the similarities and as well, and we also talk about how those are related with other words. And the real valued vectors in a predefined vector space are put. So each word is mapped to one vector, and vector values learned in with that it's represented according to the similarity, and that's how the word embedding would be formed. So let's talk about the example here. So the mouse ran up the clock. So this is the sentence, and then this is the another sentence. The mouse ran down. So in this case, we are going to form this four-dimensional embedding layer based on the similarities. So as you can see in both the sentences, we have the mouse ran same. So as you can see here, for the first three rows, you would find that the numbers are same, and that's because the words are same. So when we are going to map this uh, into the vector space, we are going to see that the similar words would be put very near to each other based on how similar those are. Uh, so let's break it down. So we have cat, kitten, dog, houses, men, women, king, and queen. So these are the words. Uh, and these are the features that we are considering here. So based, like, for each feature, we are going to put a particular score. So for, like, here we are talking about each word in terms of the features. So these are the features, as you can see, present in the columns, and these are the words present in the rows. So a cat is a living being and it's scored as this, and it's not a human, so the score is really low here. And then the gender, royalty, and verb, and that's how we are going to score cat against each of these features present in the columns. We can also see negative numbers here, and that's totally fine, because because in some cases you will be getting negative numbers when the features are not really resembling with the word. And now there is another word, kitten. So as you can see, the scores for cat and kitten are really close to each other, because kitten is kitten is essentially a cat, and that's why numbers are really close, even if these are two separate words, but the features are resembling with each other, and that's why the scores are really close. But here we have dog, and now dog is different from cat, and that's why the number would be different as well. Somehow it would still be really close to cat and kitten because dog is also an animal. uh, but that's how scoring happens. And now let's talk about men, women, king, and queen. In this case, you can see that the first feature, which is living being, would be almost same for each of these words because all of them are living being. And let's talk about something that is different for each of the words. So let's talk about royalty. So man would have a negative number here because the royalty feature would not be seen in the man. It's a term used for the king and queen, so that's why the number for king and queen is high, and it's low for men and women. And in the previous example as well, so we had positive numbers for cat, kitten, and dog because all of all of them are living beings. But we have negative number, which is a really low number for houses because it's not a living being. So that's how the numbering and how the scoring happens in word embeddings. And based on these numbers, how close these numbers are, based on that we would be mapping these individual words into a vector space. Let's see how. So we are going to use some dimensionality reduction techniques to reduce these from 7 dimensional uh, rows and columns to 2 dimensional. So as you can see here, cat and kitten are placed really close to each other because those two have had the same or like really close numbers. Dog is present far away from cat and kitten, but it's still near as compared to the houses, because houses is a really irrelevant term when we are talking about these three terms. So houses is not really meshing up well with these, so that's why it's present far away from these three words. Similarly, for man, women, and king and queen, you can see that the mapping happens according to the scores. So if the words are having close or same scores, they would be put close to each other, and if they are not same, they would be put far from each other. So there's a technique called word to vec. So word to vec is word to vector. So we are taking words and we are going to map that into vectors, and that's what we discussed just now. So this is the most famous phase of neural nets because when you're going to do NLP on a high level, when you're going to do complex tasks in NLP, in that case, the simpler techniques like pagovers and TF-IDF would not be really helpful, because in that case, let's say you have a corpus and uh, it's not really common and you have to understand the structure well. In that case, bag of words and TF-IDFs or n-grams would not be efficient and would not be helpful. And we are going to use word to vec there. So it uses a skip-gram neural network model to learn words associations, predict neighbor context from any large corpus. So we have a large corpus, and we are going to map the words, understand the relationships between the words. We are going to understand the combination, and that's how we are going to represent our corpus in a form that machine learning algorithm could understand. So each distinct word is represented as a vector, and that's what we have been doing till now. So we are considering each word as a separate vector, um, and this is this is also selected on the basis of cosine similarity. So the semantic similarity that we have been talking about till now is being calculated by the cosine similarity. So there is a cosine formula that you use to calculate the similarity in this case. So this is the vector space, and you can see how the words are being mapped here. And as you can see here as well, so these are the places, and country and capital, and like Spain and Madrid are really close. So that's how the combination would be formed. That's how the representation would be formed, and these two words would be placed close to each other when we are going to place them into the vector space. So there are different architectures in this as well. So we can think about it as substructures. So we have the root technique, which is word to vec, and then there could be two sub techniques under that. So the first one of that is continuous bag of words model. In this case, we are going to predict the current word given we already have the context of words. uh, so let's say we have a sequence of input and we want to predict the next word. So to predict the next word, we are going to understand the context and sequence based on what we already have, based on the previous words. And that's how the prediction of the current word or the next word would occur. So this is a neural network explaining how continuous bag of word models work. So there is the input layer, which is the context words, and then there is the output layer, which is the current word. We want to predict this word given we already have the sequence of these words. And there is the hidden layers, which is the number of dimensions in which we want to represent our current word. And all these things all together form the continuous bag of word models. So on a high level, there are these input words, and we are going to combine those to form the output word. uh, and opposite to that, there is skip gram model. So in previous case, we already have the context words, and we are going to predict the current word. But in this case, we have one word and we want to predict the output from that. So we want to predict the surrounding context words given we have the current word. So there is this input layer which have the current word. Then there is the projection layer. In this case, there are hidden layers and hidden dimensions in which we want to present our current words, and then the output would have the words that are being predicted based on what we have currently in the input layer. So this is many to one, and this is one to many. Phew. So that's all about the different techniques and how to represent the words into the vector space. And I'll stop for the questions. I'll stop sharing my screen, and then we'll talk about uh, how to implement those things in Google Colab. If we have any questions, please feel free to drop that into the Q&A box. Before starting the coding on the Colab notebook, let's take 2 or 3 minutes of break to digest that information. We'll start in a minute. Just give us a minute to share the screen. So finally, we are going to see how the things that we discussed in the presentation would work in coding. Uh, so we are going to implement TF-IDF and bag of words here. So this is the dataset link. You can visit Kaggle and download the dataset from there. We also showed how you can directly connect the Kaggle API to your collab in the last session. So you can revisit that as well. So in this dataset, we have 50,000 news articles. And there are articles from 5 American publications, and we are going to process this data set and see how to form the representations from words. So first, let's talk about how to access the data. So as I already mentioned, you can click on that link. You can then click on the download button. The data set is quite large, and you can download that from there. uh, One zip file would be downloaded, so you can unzip that, and you can save the file in your folder, which is easily accessible. Then just open the Google Colab notebook, and uh, on the right hand side you can see, then there is on the left hand side you can see there is the file upload button. So just click on that and upload the files that you want. As you can see that we have already uploaded these CSV files here that we are going to use today. uh, so you can do that from there. The only thing is these files would be removed when you would restart the runtime, but you can upload them again and again, or you can just use the Kaggle API. So let's start. To check which folder in the Google Colab we are currently in, we are going to use this command, which is pwd, and that shows that we are in the content folder right now. Uh, so let's see what folder we are in to see how the data would be loaded. So for that, we are going to use the command ls, and these are the files that we have right now. So next step is to load the data set and perform exploratory data analysis and pre-processing. So to load the CSV file, we are going to use pandas. So these are the columns, and we are going to read the file using the pd.read CSV command, which is the function present in the pandas library. And then we are going to apply these columns on uh, on on the data set we have. Uh, these are the columns, as you can see. Next, we are going to see how many rows and columns we have, and for that we have n row and n column. And then we are going to remove the empty rows from the CSV. So we don't want to process the empty rows unnecessarily. So for that, we are going to drop those using the drop NA function. Um, and in place is equal to true ensure that we are going to make that impact on the data directly, and we are not making any copies. So if we run the cell, we can see how many rows and columns we have. Uh, so when we run this cell, we see that how many rows and columns we have. Yeah, run. So there are 10,000 rows and 10 columns. And this is how the data frame of the data set looks like. So there are these columns, which is num, ID, title, publication, author, date, year, month, URL, and content. So we probably don't need all of these columns, but we are going to see how these columns are interrelated, or how these columns are represented, how the distribution of the labels are. So that for that we are going to use EDA, which is exploratory data analysis. We talked about that in detail in our previous sessions. So we are just going to uh, quickly see how that looks like for this particular data set. So running the next cell, we can see the top five rows with the head function, and in the next cells we can see the visualization. So before that, let's describe the data. Let's see how the individual things for our data set is. So for that, we are going to uh, just output the info of our data, which is the function present in the pandas library. And then we are going to see if there are any null values. So the is null dot sum would be the right function to do that. So as you can see that the author column has a lot of uh, null values. So we are going to probably drop that, and also the URL. Talking about the EDA now, so let's see how it looks like. So there are two publications, New York Times and Breitbart, and we can see that the New York Times is much larger than the other one. So there is the imbalanced data set here, but we are still going to process this. So running this cell would tell us the publications per year. So 2017 saw the most publications, followed by 2016, and we don't have any record for 2015 and 14. Similarly, we are just going to check out the other values as well. Running the following cells as well. We are just going to see multiple combinations and how the uh, columns are and values are spread in the data. After that, we are going to just pick the content column because most of the columns are empty or not having the relevant information. So we are just going to take the content, and for that we are going to just select that. So content DF would have the column that we want. Let's see what the content length is. So this is how the length, content length regarding number of articles is. So you can see the spread here. Next, we are going to do the part of speech tagging. So for that, we are going to import particular libraries. So NLTK is mostly used libraries for processing text, and that's what we are going to use today. And downloading the corresponding packages, process that, and we are also going to install the contractions for contraction mapping. Let's expand contractions in the next cell. So it would take a while to run because the data set is really large. So it's being applied to each and every sentence in our data set. So as you can see, it's done. Now we are going to join the list back into one string to further process it. And it's back when we have joined it together. Uh, to explore individual cells like this, we can just use the indices, and that would take us to the individual cells. Now let's talk about noise cleaning. So we discussed that stop words, punctuations, and other irrelevant stuff doesn't add much to the information and just expands our vocabulary. So we are going to clean that. So we are going to use the regex library here to remove the punctuation and the other special characters, and we are going to also make each and every word into a lowercase. So you can read the regex explanation here, how that works. It's really easy, and you can just read that from there. Then we are going to use NLTK library to tokenize sentences. So we want the sentence to be divided in separate words. So that's what we are going to do with NLTK library. So it would divide each sentence into separate words, which are tokens, and that process is called tokenization. While this is being done, where we can talk about stop words. So we also discussed that frequently occurring words like the, is, and these are not really important in the context, so we can remove them. And we are downloading the set of stop words from the NLTK library, and we would remove them from our corpus and data set. So running the stop words cell, yeah, so above you can see that the words have been tokenized, and let's see how the occurrences look like after removing the stop words in the article. So this is the function plot top stop words, and this shows uh, how the data looks like after processing. We remove the stop words, we tokenize the sentence. So this is how the data would look like. Next, we are going to import the Seaborn library, and this is like matplotlib to plot beautiful visualization plots. And here we can plot the bar charts to see the words distribution. So now just remove the stopwords using the functions that we defined above. As you can see, there are three columns. So the content is the original column that we had. Then there is the tokenized column, and then there is the tokenized content join. So we tokenized and then we joined it again. So these three columns just summed up that. So for the sake of simplicity, we are going to show only 10 article contents based on the same seed value, which is 5, so that every time you run this cell, you get the same results. So that's what random state is used for. Finally, we have TF-IDF technique. So we talked about the working and the formulas already in the presentation. So we are just going to use the particular library and perform that. There is already a function present in the scikit-learn library. You can read the documentation here, and we are going to import that from the library. So from scikit-learn dot feature extraction, we are going to import TF-IDF vectorizer. So these are the arguments. So each argument have a different meaning. So for the sake of simplicity, you can just define nothing and just pass in your data. It would do the things automatically. But max TF is to draw words that occur in more than X% of documents. So for that, for this case, we are taking 30%. And similarly, there's MinDF, which only use words that appear at least X times. So here we have 8. Stop words are mentioned in English, so we are mentioning English here. Lowercase is equal to true means that we want to convert the words into lowercase so that there is no redundancy. Use IDF is equal to true is for using the IDF. Norm u 12 is for the normalization. Smooth IDF true is to prevent divide by zero errors. So after running this cell, we would have the TF-IDF vectorizer ready, and we can just fit transform that on our content subset, the column that we are going to process. So let's see how that looks like. So these are the numbers. So these are the TF-IDF scores for each of the unique words that we have uh, displayed here. So that's how the data would be sent to the algorithm now. So it's not text anymore, and it's easy to process. So to check the shape, you can run the shape property here, and you can see the vocabulary. And now let's talk about the another technique, which is bag of words. So in bag of words, as we discussed, that we have the raw data and we just get the vectors based on the frequency of each words. So that's what we are going to get now. So content DF. So we have tokenized content join column. We are going to take that, and from the scikit-learn again, we have count vectorizer. So we are going to import that. We are going to fit transform that on our corpus, which is our data set. And while printing, we can see that this is how the numbers are assigned to the words based on the So these are the feature names, and then when we print the two array function, we can see these are the numbers based on the frequency. So 1 represents that the word has occurred one time, 0 represents that it hasn't occurred, and 2 represents it has occurred two times. So let's see how to output that with the dense function. Finally, repeat the analysis but with a larger subset of the data. Running the cells again, the logic is same, just we are taking the larger subset of the data. After running all these cells, we are just going to call the count vectorizer function. So here we also have the n-gram range, and you can set that accordingly. We already discussed what n-gram is. And next we are going to just print the feature names. So it would take a little bit of time because now we are taking a larger data set. So it would take some time to. After it's done, we are just going to run the corresponding cells and see how that looks like in the array. So, so that's all for now. So you have seen that how bag of words and TF-IDF works. And for references and for the further reading, we have put the additional cell here, so you can refer to these resources present in this cell to uh, dive deeper into the concepts. So that's all for the coding part today. Uh, the ending, so we can just end here. So today we learned about text representation and feature engineering, and in the coming sessions we are going to talk about modeling. So till now we have processed the data and we have passed that, and in the next session we are going to see how to pass that to the real algorithm and how to make predictions. We talked about the NLP pipeline. So we are going to see you in the next session now, which is going to be on machine translation and conversation, which is on December 13th at 7. Uh, Thank you so much, everyone, for joining in. You can join us on Slack. You can ask us questions there. These are the upcoming events that you can register for. Uh, and if you have any questions, you can join our Slack and ask the questions there. You can find the notebook on the Women Who Code GitHub repositories. And also make sure to follow us on social media handles. Thank you so much for joining in, and we hope you have a great week. Or thank you so much.
Thank you all for joining.